Hello everyone, myself Vikas Kumar and I'm studying in Sri Venkateshwara College of Engineering and the branch is IC, USN is 1V22 IS060, subject is discrete mathematics, topic is Lagrange's theorem. Lagrange's theorem, a fundamental principle in a group theory. Lagrange's theorem is a fundamental theorem in a group theory, a branch of abstract algebra that studies algebraic structures called groups. The theorem establishes a crucial relationship between the order of a group, the number of elements in the group, and the order of its subgroup. It provides a powerful tool for understanding the structure of groups and has a numerous application in various areas of mathematics including cryptography and coding theory. This presentation we will delve into the intricacies of Lance theory, exploring its definition, condition, proof, application, and implications in the realm of group theory. Definition of Lagrange's theorem. Lagrange's theorem states that for any infinite group G, the order of subgroup H of G divides the order of G. In other words, if order of G represents the order of group G and order of H represents the order of subgroup H, then H divides G. This is a theorem's fundamental results in group theory, as it establishes a relationship between the size of group and size of its subgroup. First one, order of a group. The order of a group is the number of elements in the group. Order of subgroup. The order of subgroup is the number of elements in the subgroup. Third one, divisibility. One number divides another number if the first number goes into the second number evenly without a remainder. Finite group. A finite group is a group with a finite number of elements. Conditions for Lagrange's theorem. Lagrange's theorem holds true for a finite group. This means that a theorem applies to any group that has finite number of elements. It does not apply to infinite groups, which have an infinite number of elements. To illustrate this, consider a group of integers under addition. This group is infinite and it has subgroups of various size such as the group of even integers, the group of odd integers, and so on. However, the order of these subgroup does not divide the order of the group because the group itself has an infinite order. Finite group. Lagrange's theorem applies to the finite groups which have finite number of elements. This means that the group itself and all its subgroups have specific countable numbers of elements. Subgroups. The theorem dwells into the subgroups which are set of elements within a group that themselves form a group under the same operation. Every group contains at least two subgroups, the group itself and the trivial subgroup, and containing only the identity element. Order. Lagrange's theorem focuses on the number of groups and the order of its subgroups. The theorem asserts that the order of any subgroup must divide the order of entire group. Proof of Lagrange's theorem. The proof of Lagrange's theorem relies on a concept of cosets. A coset A of subgroup G is in group G is a set obtained by multiplying all the elements of H by a fixed element G in G. Cosets play a crucial role in understanding the relationship between subgroups and groups. The proof involves showing that the cosets of a partition G into a equal sized subset, each containing H elements. This leads to the conclusion that order of H divides order of G. Cosets. For a subgroup H of a group G, a coset of H is set formed by multiplying each element of H by a fixed element in small g in capital G. Partition. The coset of H partitions G into disjoint subsets, each containing the same number of elements as H. Divisibility. Since G is partitioned into equal subsets, the order of H must divide the order of G. Applications of Lagrange's theorem. Lagrange's theorem has significant applications in various fields of mathematics, particularly in cryptography. It is a role in coding theory is equally important. By applying the Lagrange's theorem, we can determine the number of possible keys for cryptography based on the order of the group associated with a cipher. This ensures that the number of possible keys is sufficiently large to make a brute force attacks impractically. Cryptography. Lagrange's theorem helps determine the number of possible keys in the cryptographic system, making it as a fundamental tool for security analysis. Coding theory. Lagrange's theorem aids in understanding the structure error correcting methods, correcting codes which are used to detect and correct errors in the data transmission. Group theory. Lagrange's theorem provides a powerful tool for investigating the structure of groups and understanding the relationship between the subgroups and the groups. Relationship to a Fermat's little theorem. Fermat's little theorem is a special case of Lagrange's theorem. It states that for any prime number p and any integer not divisible by p, a raised to power of p minus 1 leaves a remainder of 1 when divided by p. This can be derived from Lagrange's theorem by considering a cyclic group of integer modulo p, where the order of group is p. The order of the element a in a subgroup is p minus 1, and therefore Lagrange's theorem a to the power of p minus 1 leaves the remainder 1 when divided by p. Fermat's little theorem. For any prime number p and integer a not divisible by p, a to the power of p minus 1 leaves a remainder of 1 when divided by p. Lagrange's theorem. For any finite group G and subgroup H of G, the order of H divides the order of G. Connection. Fermat's little theorem can be viewed as a special case of Lagrange's theorem applied to a cyclic group of integers modulo a prime number. Generalization of Lagrange's theorem. While Lagrange's theorem applies to all infinite groups, its generalization extends its applicability to infinite groups. This generalized version states that for any subgroup H of G, the order of H divides the index of H in G. The index of H in G is the number of left or right cosets of H in G. The generalization provides a way to apply the core idea of Lagrange's theorem to the group with an infinite number of elements, broadening its scope and influence in the group theory. Finite group. Lagrange's theorem applies to a finite group where both the group and its subgroups have finite number of elements. Infinite groups. The generalized version of Lagrange's theorem extends to its applicability to infinite groups, providing the insights into their structure. Index of a subgroup. The index of a subgroup H in a group G is the number of left or right cosets H in G. Divisibility. The generalization states that the order of H divides the index of H in G, similarly to the original theorem concept of divisibility. Importance of Lagrange's theorem. Lagrange's theorem is a cornerstone of a group theory, providing a fundamental tool for understanding the structure of groups. It establishes a direct relationship between the order of group and the order of its subgroups. This connection allows us to deduce properties of subgroup based on the order of groups and vice versa. The theorem plays a crucial role in solving various problems in group theory and significant applications in other areas of mathematics and science. Structure of groups. Lagrange's theorem helps understanding the relationship between the size of a group and the size of its subgroups, providing insights into the group structure. Subgroup properties. The to theorem allows us to reduce the properties of subgroups based on the order of groups, making it a powerful tool for analysis. Application. Lagrange's theorem has a broad applications in the field like cryptography, coding theory, and other branches of mathematics. Limitations and exceptions in Lagrange's theorem. Well, while the Lagrange's theorem is a powerful tool in a group theory, it does have some limitations. The theorem does not guarantee the existence of subgroups of every possible order, dividing the order of subgroup. For instance, there exists a group where the order of a group is divisible by a prime number, but the group does not contain a subgroup of prime order. These limitations provides valuable insights. It a, does not offer a complete picture of the structure of all the groups. Divisibility. Lagrange's theorem guarantees that the order of any subgroup divides the order of a group, but it does not guarantee the existence of a subgroup every divisor of the group's order. Non-normal subgroups. Lagrange's theorem applies only to the subgroups that are non-normal. Non-normal subgroups may not satisfy the divisibility relationship stated in the theorem. Conclusion and summary. Lagrange's theorem, a fundamental principle in the group theory, establishes a crucial relationship between the order of a group and the order of its subgroups. It states that the order of any subgroup divides the order of a group. This theorem has numerous applications in various areas of mathematics, particularly in cryptography and coding theory. While its limitation and does not guarantee the extinctions of subgroups for every possible order, it provides a powerful tool for understanding the structure of groups and has contributed significantly to the advancement of group theory. The theorem influences extends beyond the abstract algebra, finding application in various scientific disciplines. Its ability to connect the size of a group to the size of its subgroups has made it a cornerstone of group theory and a valuable tool for mathematicians and scientists alike. Thank you.